I want to start talking about circle theorem, and the first one I want to talk about is that the angle in a semicircle is 90 degrees. Let me just demonstrate that to you. Angle in a semicircle, 90 degrees. Okay. You can see that's the diameter which goes through the middle, and you've got a triangle here. You've got a triangle within this semicircle. I'm just going over it. That's my semicircle, so that's the angle within the semicircle. No matter where I take it, it still remains 90 degrees. Okay, it looks like I've broken it there, but you can imagine that's 90 degrees in there. That's the outside 270. But anyway, let's move that. You can see it remains at 90 degrees no matter where I take it. I'm stuck. Angle in a semicircle is 90 degrees. This one's a different circle theorem. So you've got your circle. See that line there? That's a tangent. A tangent sits on a circle. You can see that tangent is just sitting around that circle. And here you've got the radius. And it goes like this. The tangent and radius makes 90 degrees. So that corner there is 90 degrees. And same on the other side. That's 90 degrees as well, no matter where I take it. With this one, we can say angle at the center, that 80 degrees there, is twice the angle at the edge. No matter where I take it, look, still double. The center is twice that of the edge. I can change it maybe. Right. You see? Now sometimes they might give you a question like this. It looks like this. It's hard to recognize that this is angle at the center twice the angle at the edge. This one kind of looks like a rocket. So that 100 degrees, right? That's the bottom of the rocket, and you got the top of the rocket. But then your rocket could be distorted like this. But that's still angle at the center is twice angle at the edge. One thing you need to be wary of is that, right, I've just said angle at the center, that one there is twice that angle here. But what if they give you this angle instead on the edge side? Let's say they call that 300 degrees. That one there, 300 degrees, and they expect you to work at this. Well, you can't just half 300 to get 150. That's not going to work. You need this angle. And you know, angles around a point add up to 360 degrees. So you know, this is going to be 60 degrees. Then you can say, angle at the center is twice the angle at the edge. That makes this one 30 degrees. Now, you need to be careful with these type of questions as well. You might be fooled into thinking that angle at the center is twice the angle at the edge here, but that doesn't apply. That theory doesn't apply here, because you can see that angle here is not at the center. So whatever I said here about angle being twice the size at the center compared to the edge, it will not work for this. Right, this one is a cyclic quadrilateral, four-sided shape. And you notice all four corners, vertices, are sitting around the edge of the circle. One thing you'll notice though is that the opposite angles in this cyclic quadrilateral add up to 180. So that 120 and 60 adds up to 180. If I change that, you can see it still adds up to 180. And likewise, place where I'm pointing right now, this one and its opposite end, that one, would add up to 180 as well. Now, this one might look like a cyclic quadrilateral. It's not, because one of the corners is not touching the edge of the circle. It's just 3. It has to be all 4. Right, this one looks fairly tricky. It's called the alternate segment theorem. What you're looking at is for a tangent that's connected to a triangle on the edge of the circle, like here, right here. Now you can see what's happening. This number 62, 62 are identical. No matter where I take it, it's the same. Right. This one is fixed at 40, so that's why this one is fixed at 40. It's when I change this over here, the tangent, the location of the tangent, the values change, but they are the same. Now if you just follow my cursor, you might think, okay, here I've got a Z, just tracing a Z with the cursor. So you might think that this is 45 where my cursor is. It's not. If you've recognized it's the alternate segment theorem, look for the Z, like I've just traced now. The 45, this is not going to be 45, it's on the other side of the triangle. So always remember that. And once I've recognized that this is the alternate segment theorem, i.e. triangle with a tangent joined to it on the edge of the circle, I've got an angle here. You might think, well, that looks like a Z, kind of like an alternate angle, except you can't guarantee that this is parallel to that, so do not assume it's anything to do with alternate Z angles. Right, so this is 60, do not assume this is 60. This being the alternate segment theorem, it's the other side, that's 60. So this one here matches this one. Now let's suppose we have this one as 70 degrees. Where's the other 70 degrees? Well, clearly it can't be this one. These are not matching anyway, it has to be on the other side. This one is, it's got two tangents. Here's another one, meeting up together on the outside of the circle. So two tangents to a circle have the same length, as you can see here. The perpendicular bisector of a chord always goes through the center of the circle. So that blue line there is a chord, right? That's a chord. And that black line there is a perpendicular bisector of that chord, meaning perpendicular means right angles. See the blue line and the black line at right angles, so they're perpendicular to one another. And bisect means cut in half. That black line has cut the chord in half. That black line is guaranteed to go through the center of the circle, as you can see. So to say it again, the perpendicular bisector of a chord always goes through the center of the circle.